Every single AI project you've ever heard of, from a chatbot to a self-driving car, it has this life cycle that's split into two completely different phases. There's the part where it learns, and then there's the part where it actually works. And understanding this divide, well, it's the key to understanding how AI is built, how it's deployed, and most importantly, where the real money is spent. And trust me, the answer is probably not what you think.
So here's the best way to think about it, and we're going to stick with this analogy the whole time. Think of AI training as the model going to school. It's this super intense upfront period of just learning, learning, learning. AI inference, on the other hand, is when the model graduates and gets a job. It's out there in the real world doing its thing day in and day out. School versus the job. That's the fundamental split we're going to unpack.
So here's the plan. First, we're going to dive into the school phase, the training. Then we'll see what happens when it gets a job during inference. After that, we get to the real heart of it, the hidden economics and why that job can end up costing way, way more than the schooling. And finally, we'll look at some of the clever tricks engineers are using to keep those costs under control.
All right, let's start with phase one, the training. This is all about building the AI's brain. It's this massive behind-the-scenes effort. Think of it like cramming years and years of education into this intense computational boot camp that happens long before you or I ever get to interact with the model.
So how does this schooling actually work? Well, first, the model just ingests an unbelievable amount of data. We're talking petabytes, huge chunks of the internet. Then comes the hard part, finding patterns. It uses a process called backpropagation, which is really just a fancy way of saying it learns from its mistakes over and over and over again, adjusting billions of little internal knobs. And this cycle just repeats, sometimes for weeks on end, on these massive supercomputers, until the model finally builds a generalized knowledge of its world.
And here's the crucial takeaway for this phase. Training is what we call a compute-bound process. It's all about brute force. The biggest thing holding you back is just the raw horsepower of your hardware. Success is all about throughput. How much data can you possibly cram through the system per second? It's this incredible sprint that feels like a marathon, pushing thousands of GPUs to their absolute breaking point.
And you've got to understand, this is a totally new way of building software. The AI expert Andrej Karpathy put it perfectly. He said, we're not just making another classifier, we're making software 2.0. Instead of writing explicit line-by-line code, we're essentially programming with data. The training process is what lets all that data write the software for us, shaping the brain of the neural network. Okay, so school's out. The AI's training is done. Now it's time for phase two, inference. The model has graduated, and it's time to put that brand new brain to work out in the real world. This is the moment you type a prompt into a chatbot, or an autonomous car sees a pedestrian, or a spam filter looks at a new email. Now, when it comes to inference, the single most important thing is latency, basically the AI's reaction time. See, unlike training, which can take days, inference has to feel instantaneous. For any real-time app, we're talking milliseconds. If you have to wait for a chatbot to think, or a self-driving car hesitates for even a second, the whole thing just falls apart. Speed isn't a feature, it's the entire point. And that latency is really made up of two key parts. The first is time to first token, or TTFT. This is all about how quickly the AI starts responding. A low TTFT is what makes an app feel alive. It's that instant feedback that tells you, yep, I heard you and I'm on it, even if the full answer takes another second to generate. The second part is time per output token, or TPOT. This is the speed of every single word that comes after the first one. A good TPOT creates that fluid, natural stream of text that feels like a real conversation. So you put TTFT and TPOT together, and that right there defines the entire user experience. And here is the absolute critical difference from training. Inference is often a memory-bound process. The bottleneck isn't raw calculation anymore. It's how fast you can shuttle the model's parameters, which can be hundreds of gigabytes, from the GPU's memory over to its processing cores, just to generate a single word. A lot of the time, the processor is just sitting there, waiting for the data to arrive.
Okay, so we have compute-bound training versus memory-bound inference, the school versus the job. Why on earth does this technical difference matter so much? Well, because it has absolutely massive consequences for the hidden economics of AI. This table just lays it all out, side by side. Training is this giant one-time capital expense, a big CapEx hit to buy all that hardware. But inference? That's a non-stop, ongoing operational expense, an OpEx that runs every second of every day. Training can take its time, but inference demands a response in milliseconds. They are, for all intents and purposes, economic and operational opposites.
And this all leads to what is probably the single most staggering statistic in the world of AI operations. While training gets all the headlines for being so expensive, it's inference, that day-to-day job that can account for 80 to 90% of a model's total lifetime cost. Yeah, this visual makes it crystal clear, doesn't it? That huge one-time training cost is just dwarfed by the relentless day-after-day cost of running the model for millions of users. Inference is the silent killer of AI budgets. And the crazy part is, the more successful your app becomes, the bigger this problem gets. And it's not getting any better. As the AI pioneer Jan LeCun points out, as these models get smarter, inference doesn't get cheaper. It actually gets heavier for each question you ask. It makes sense, right? It takes way less brainpower to answer what's the capital of France than it does to write a 10-page business plan. Smarter models mean more expensive answers.
So if inference is where all the money is going, how in the world do we control it? This brings us to our final section, taming these hidden costs. It's a huge engineering challenge, and it's all about designing a long, productive, and cost-efficient career for your AI. Engineers have a whole bag of tricks for this. They do things like quantization, which is like shrinking the model by using simpler numbers. Think rounding 3.14159 down to just 3.14. Or pruning, where they literally snip away unimportant connections in the AI's brain to make it leaner. And then there are other smart techniques like continuous batching, which is kind of like creating a carpool lane for user requests to make sure the expensive GPUs are always busy. It's all about making that job as efficient as possible.
Andrew N. really nails the new reality we're in. The frontier isn't just about building bigger and bigger models anymore. It's about smarter orchestration, about managing the entire life cycle and making intelligent trade-offs between that big upfront training cost and the massive ongoing cost of inference. And that really leaves us with a final thought. The measure of a truly great AI system isn't just its raw intelligence anymore. The real question, the one that's going to decide which AI products win or lose, is this: how efficiently can it work? It's that balance of intelligence and operational excellence that's going to define everything that comes next.